In this video, we are going to define current density with its unit and state an expression to solve problem based on current density. So current density can be defined as the current flowing per unit area. So if you have a conductor that has a current I flowing through it, the amount of current that passes through a given area within a conductor is defined as the current density. We represent current density with the letter capital J, and you can write as the amount of current flowing per unit area. Now, since current I is measured in ampere, area is measured in meters squared, the unit of current density is ampere per meter squared, or you can also write this as coulomb per second meter squared, as ampere can be written as coulomb per second. The conversion between units is very important to understand as they can be asked as multiple choice in exams. Then you can rewrite the same expression to write I to be equal to J times A, or in integral form you can write the same thing as I to be equal to integral J bar dot A bar. Now current density is a vector quantity, and since current is a dot product of two vector, current itself becomes a scalar quantity. So although current has a direction, but it is still a scalar quantity because we do not add current using vector algebra, we just add them using scalar addition, whereas current density on the other hand is a vector quantity. You can also relate current density to drift velocity. We know the current I is dq over dt, and you can write this current I in terms of drift velocity as negative ne drift velocity into the area. This gives me current density J to be equal to I over A. So that becomes equal to negative Ne Vt A over A. So current density J becomes equal to minus Ne Vt, where E is the elementary charge of proton or electron, Vt is the drift velocity, N is the number of electrons passing through a given area, and the negative sign only represents that the flow of electron is opposite to the flow of current. So if the current here is going to the right, electrons will flow to the left and hence the negative sign. So now let's apply this rule to solve problem. First question says, what is the current density in an aluminum wire having a radius of 1 millimeter and carrying a current of 1 milliampere? So here in this question, we have a wire that has a radius r of 1 millimeter, which you can write as 1 times 10 to the power negative 3 meter. The current flowing through the wire I is 1 milliampere, which is 1 times 10 to the power negative 3 ampere. We need to find the current density J. So we apply the rule J is equal to I over A. Area of a wire, since a wire is in the form of a cylinder, its cross-sectional area is a circle, and area of a circle is pi r squared. So we write this as I over pi r squared. Now let's substitute. I is 1 milliampere, so 1 times 10 to the power negative 3 over pi times R is a term with a multiplier. So you take 1 times 10 to the power negative 3 and then square them both. Whenever a quantity is multiplied with a multiplier or a term with a power, make sure you square both the terms in that quantity and not just the value. So after you solve this, you get current density J to be equal to 318.3 ampere per meter squared. Next question. A conductor carries a current of 50 microampere. If the cross-section area of the conductor is 50 millimeters squared, then the value of current density is. So here you have I to be equal to 50 micro. So micro will be 10 to the power negative 6 ampere. Then you have area of cross-section to be 50 millimeters squared. Now milli is 10 to the power negative 3 meter, and then you take square of this term. We take square only of the multiplier to convert it from millimeter squared to meter squared. I need to find current density J. So we use the rule J equals I over A. I is 50 times 10 to the power negative 6. A is 50 times 10 to the power Negative 3 squared will be negative 6. So when you solve this, you get J to be equal to 1 ampere per meter squared. So the correct answer will be option D. Then we have a current of 0.12 ampere flow in a silver wire whose cross-sectional radius is 3.2 millimeter and resistivity is 1.62 times 10 to the power negative 8 ohm meter. We need to find the current density in the first part of the question. So we write I to be equal to 0.12 ampere. Radius R is 3.2 millimeter, which will be 3.2 times 10 to the power negative 3 meter. Resistivity of silver is 1.62 times 10 to the power negative 8 ohm meter. We need to find the current density J. So we write J as I over A. Cross-sectional area of the wire is pi r squared. So let's substitute 0.12 over pi times r is 3.2 times 10 to the power negative 3 squared. Make sure you take the whole term in the bracket and then you do the squared. That gives you the value of J to be equal to 3730.2 ampere per meter squared. In the second part, they want us to find electric field in the silver. Now, there is a relationship between electric field, resistivity, and the current density, which is given as rho equals E over J. So I can find E as rho times J. So let's multiply them. Rho is 1.62 times 10 to the power negative 8. Current density is 3730.2. And when you solve this, you get the electric field to be equal to 6.04 times 10 to the power negative 5 volt per meter. Then in the next question, you have a copper wire that has a diameter of 0.05 centimeter. It is attached to an aluminum wire of diameter 0.01 centimeter. The same current flows through the two wires. Calculate the ratios of current densities in the two wires. So here you have two wires. One of them is made up of copper. The other one is made up of aluminum. And they are both attached together. The same current I flows through them. We need to find the ratio of their current density. Given the diameter of copper wire is 0.05 centimeter and the diameter of aluminum wire is 0.01 centimeter. Now we know that current density J is given as current per unit area. So I can find current density for copper to be equal to I over area of copper and current density for aluminum to be equal to I over area of aluminum. So let's take their ratio. J for copper over J for aluminum will give me I over A copper, then I over A aluminum. Now let's cancel off the I here. And then we rewrite this as J of copper over J of aluminum to be equal to area of aluminum over area of copper. Now cross-sectional area of a wire is given as pi r squared. Now in place of r, we have the diameter d. So I can rewrite this area in terms of diameter as pi d by 2 squared because r is d by 2. So that gives me pi d squared by 4. So let's substitute pi d aluminum squared by 4 over pi d copper squared by 4. Cancel off the pi, cancel off the 4. You are left with diameter of aluminum squared over diameter of copper squared. Now let's substitute. You get 0.01 squared over 0.05 squared. Now since this is the ratio of the term with the same unit, I don't have to convert the unit from centimeter to meter. We can just keep them as centimeter as the units will cancel off. And when you solve this, you get the answer to be equal to 0.04. Or you can also write this as 1 over 25. So this is the ratio of current densities in the two wires. Next question. Two wires X and Y. X with cross-sectional area equal to 5 times 10 to the power negative 5 millimeter squared and Y with cross-sectional area equal to 3 times 10 to the power negative 5 millimeters squared, if the two wires are carrying the same current, which of the following is correct about their current density J? So again, we need to find the ratio of their current density to find the correct relationship. We know that current density J is I over area. So I can write current density for X to be equal to I over AX, whereas current density for Y will be I over AY. Same current I flows through the two wire. Now let's take the ratio. I write JX over JY to be equal to I over AX, I over AY. We cancel off the i's here. This ratio will become equal to AY over AX. So we get JX over JY to be equal to AY over AX.
Now this relationship you can use whenever they ask you to find ratio of current density. We know that current density is inversely proportional to area, so Jx over Jy has to be equal to Ay over Ax. So if we have two wire 1 and 2, the ratio of current density will then become J1 over J2 equals A2 over A1. They must go opposite to each other.
I need to rewrite everything in terms of Jx, so let's rearrange. Jx will be equal to AY over AX into JY. So let's substitute to calculate the relationship. We get Jx to be equal to AY is 3 times 10 to the power negative 5. AX is 5 times 10 to the power negative 5 into JY. Again, since this is a ratio of terms with same unit, I don't have to convert from millimeter squared to meter squared. So cancel off the common terms. You get Jx to be equal to 3 over 5 Jy. So the correct answer will be option D. Then in the next question, you have which of the following is not true for current density J and current I. So here in this question, they are asking you what is not true. That means which is not correct for current density. And please be very careful with this kind of question and look at the keyword, whether they are asking you what is true or what is not true. Now, current density is defined as J equals I over E. And then we can rewrite I to be equal to J into A. And from this expression, we know the unit of current density is ampere per meter squared. So out of this option, option A is correct. Option B is also correct. Option C says the unit is ampere per meter squared, which is also correct. Then we have option D that says current density is equal to ampere per meter, which is an incorrect statement. So this should be my answer, option D.